Let's look at Chapter 9, Section 1, problem number 19, and work that one. Here it is. Children in 2 elementary school classrooms were given 2 versions of the same test, but with the order of questions arranged from easiest to more difficult in A and reverse order in B. Randomly selected students from each class were given version A and the rest version B. The results are shown in the table. Okay, so right off the bat, let's check and see what conditions we have here. We talked about the randomly selected students. That gives us the independence between the 2 groups. And we also have here in our version A and B, the number in our sample is both greater than 30 for both of these samples from these separate populations. So that means we should be able to use the standard normal type version of, or normal assumption on this particular one when we get into the specifics on the problem. Okay, then we have our version A and B, which I'm going to use as version 1 and 2 for our samples for 2 different populations. So A, construct a 90% confidence interval. Sounds like the normal thing we've seen in the last 2 here in this section of Chapter 9. So 90% confidence interval, so our alpha is going to be 0.10. For the difference in the means of the populations of all children taking version A of such a test and all children of B of such a test. Okay, these 2 different versions, so we're going to look at the difference in these 2. What's the confidence interval on that difference. So let's go to our equations here that we have for that. As I mentioned, since I was looking at independence and sample size, allows us to use the confidence interval equation where we're looking at the difference in the sample means, x1 minus x2 plus or minus z, and alpha over 2 times the square root of that beastly standard deviation squared over the sample size plus the standard deviation of the second sample squared over its sample size. So we've done this several times already. Let's continue by several times. If you've watched the questions number 13 and 15, you've seen those different times. So if we substitute in our values for these, we've got, let's see, our 83 on the 1 minus 73 plus or minus z at 0.10 over 2, the square root of our standard deviation squared divided by the number in the sample plus our standard deviation squared divided by the number in the sample. And now we look up values for z and work out all of these values here. And I just noticed that when I wrote down the x2 bar, the standard deviation of the second one, I put 73. That should be 78. So 78. All right. So let's continue here. So as we start working at this will be 5 plus or minus, this will be z of 0.05. And again, like we mentioned, you can look that up in the cumulative standard normal table or the t-distribution table with degrees of freedom at infinity, where the t-distribution is equivalent to the standard normal distribution, which is what I did for this one. So that value, when I looked that one up, was, I wrote it down somewhere here, 1.645. You've seen that one multiple times. Times the square root of this beast, which winds up being 0.683 plus 0.578. So we're going to have 5 plus or minus 1.645 times, oops, let me do it this way. When I do that square root, I get 1.645 times 1.123. So we're going to have our, this will be 5 plus or minus 1.85, or our confidence interval of 3.15 to 6.85. So there's our 90% confidence interval for the difference of these 2 sample means. Okay, so B, let's now test this, the hypothesis at a 1% level of significance, so 1% level of significance. Our alpha is going to be equal to 0.01 here. And that the hypothesis that the A version of the test is easier than the B version of the test, even though the questions are the same. So interesting one here. So how do we interpret that? So for our null hypothesis, so our mu of A minus mu of B. So let's see if it's easier. Okay, then so easier. If it's easier, you get a higher score. So A would be higher score and B would be lower score because it's harder. So if we have our average sample there, so A should be greater than B. So A minus B will be, so our null hypothesis is that they're the same, there's no difference. And our alternative hypothesis is going to be that A is greater than B, so the difference is going to be greater than 0. There we go, so there's our step 1 hypothesis testing, determine our null and alternative hypothesis. Okay, let me give us a little more space on the screen here so as we continue through this. Let's see, questions are the same. Step 2 is determine our test statistic. And we mentioned previously when we were doing the confidence interval that the sample size, etc., allows us to look at our test statistic here being a z-value. And the test statistic from the equation is our x1 bar minus x2 bar minus our d0. In this case, the d0 is going to be 0. So our difference of the null hypothesis, d0. And then again, we have that's divided by the square root of the first sample standard deviation, the second standard deviation sample squared, and both of those are each divided by their own number of pieces in the sample, number of units in the sample. And again, we calculated some of these already. We have this x bar minus x2. That one was up here. And we have our statistic down here of the whole square root thing. That's over here. So let's go ahead and pull those out. So this is going to equal 5 minus 0 over, where was that statistic thing? Oh, 1.123. I could find it there somewhere, which gives us 4.45. So that was actually doing our test statistic and calculating our test statistic. That's so 2 and 3 in our steps for our hypothesis testing. Step 4 then is calculating the confidence interval, critical value. So our rejection intervals for this problem at our level of significance. And so we're going to do a z at 0.01. And when we look that one up on our table, that is 2.326. So our critical region is going to be at 2.326 to infinity. And we see that our calculated z is greater than our z at 0.01, or it's in that, or this is in that critical region. And as such, then, for our conclusion from this, that we do. So we do reject the null hypothesis at our 1% level of significance, that they're the same. So we're saying that yes, we have statistical evidence to say that the mean of the test done in sequence A is greater than the mean of the test in B because the difference is greater than 0. Okay, all right, let's look at if we compute the observed significance. So observed significance of this test. So the test value, so our z at the level, the p-value was 4.45. So our p-value, the level of significance for this test, will be what probability gives us the 4.45. So if we look inside or inside the table at the 4.4. No. Given our 4.45 for our z-value, do that on the outside. Inside the table is our probabilities on the cumulative normal standard distribution table. So there, that gives us a probability value of way out there at 0 on the table, which means way out there in some significant digits with some place with lots of zeros out there. There's some value that would give us what this one is. So essentially, our p-value is 0. There.